Good morning and welcome to this lesson dedicated to electrical properties of materials that is given in the frame of the class Materials and Their Properties of the Federal University of ABC. So in this class, we are going to remember important parameters and equations related to electrical conductions, which are the Ohm's law, conductivity, and resistivity. Then we will present electronic conductions in materials and its relation with the electronic energy band structures in materials, in the different classes of materials, in metals, insulators, and semiconductors. And we are going to also introduce ionic conduction that is found in ionic ceramics. So let's first introduce the resistivity and conductivity, and let's consider the following electrical circuit. So in this circuit, we have a battery, which is a power source. We have a variable resistor from which we can change the resistance, and we place a ammeter to measure the current that is flowing into this circuit. Then we are going to place a specimen of a material from which we want to know the electrical properties. This specimen has a specific dimension. It has a length, L, and a cross-sectional area, A. And we are going to use a voltmeter in order to measure the voltage drop between this point and that point of the specimen that are separated by the length L. And so we can refer to the Ohm's law that states that the current I through a conductor between 2 points is directly proportional to the voltage across the 2 points. And the constant of proportionality, R, is the resistance of the specimen, and it is an extrinsic property, which means that it depends on the specimen configuration. So the resistance of the specimen is given in ohms. In order to get rid of this dependency of the specimen configuration, and in order to present a parameter that is intrinsic property of the material, we introduce the resistivity. So the resistivity is equal to the resistance of the specimen times the area of the cross-section, which is perpendicular to the direction of the current, and L, which is the length between the 2 points at which the voltage is measured. So the resistivity is an intrinsic property of the material, and it is given in ohms per meter. So we can also define another parameter that is useful, which is the electrical conductivity, which is the reciprocal of the resistivity. So its unit is ohm meter inverse, or Siemens per meter, and the electrical conductivity indicates the ease with which a material is capable of conducting an electric current. And so the resistivity and electrical conductivity are two parameters that are independent of the specimen geometry and are properties of the material. So by combining this equation, we can also express the Ohm's law in a different way that is written right here. So in this equation, we have the relationship between the current density, J, which is in ampere per square meter, and the electric field intensity, which is in volt per meter. And the coefficient of proportionality is the electric conductivity. And so depending on the value of the electrical conductivity or resistivity, either one or another, we can classify the materials in three categories. So we will have conductors, which electrical conductivity is higher than 10 to the power 7. Then, so in this category, we will find silver, copper, aluminum, platinum, bismuth. So we will find metals. Then we have the category of semiconductors, which electrical conductivity range from 10 to the power 4 and 10 to the power -6. So we have germanium, silicon, gallium arsenide, gallium phosphide, cadmium sulfide. So they have intermediate conductivity between the one of conductor and the one of insulators, which represent the last category. So insulators will be materials that will have an electrical conductivity lower than 10 to the power -10. So glass, nickel oxide, diamond, sulfur, fused quartz, but also the majority of polymers are in this category of insulators. Now let's introduce electronic and ionic conduction. So an electric current results from the motion of electrically charged particles in response to forces that act on them from an externally applied electric field. So globally, the positively charged particles are accelerated in the field direction, whereas the negatively charged particles are accelerated in the opposite direction. And so what do we have in our material as charged particles? We have electrons, which are particles with a negative charge of -1.6 10 to the power -19 Coulomb. We have hole, which are missing electron from the valence band, which is a particle with a positive charge, but so it is the charge of 1.6 to 10 to the power -19 Coulomb, and cations and anions in ionic materials, which are negative and positive charge, which are multiple of the net charge of an electron. And so depending on the kind of particles that will flow in the material, if the current arises from the flow of electron, we are going to talk about electronic conduction, whereas that if the current is due to the net motion of charged ions, we are going to talk about ionic conduction. In this lesson, we are going to focus on electronic conduction, since the majority of insulators, conductors, and semiconductors have their electrical conduction explained through this mechanism. And the focus, the magnitude of the electrical conductivity is dependent on the number of electrons available for electrical conduction. And so to explain, to understand which electrons are available for electrical conduction in a material, we need to remember the arrangement of the electron states and the manner in which these states are occupied by electrons. At the beginning of this class, we introduced the energy band structure for isolated atom. And so let's remember, we introduced that 4 quantum numbers unable to explain the position of the electrons in the energy states. And so we describe, first of all, the shell, the first quantum number, which is given by an integer. So 1, 2, 3. And then we introduce the subshells that are designated by the letter S, P, G, and the magnetic orbital quantum number. And finally, we said that the electron fills the states having the lowest energy, and 2 electrons of opposite spin will occupy these states. But of course, a material is not composed of isolated atoms. They are composed of many of them. So a solid consists of n atoms, originally separated and brought together in order to form bondings. And so in this graph is represented the different energy levels as a function of the interatomic distance. In that case, let's think that the material is composed of 12 atoms. So when these atoms are far from another, one atom will have the electronic state, the electronic structure that we describe for the isolated atom. So in that case are represented the 1s electronic state and the 2s electronic states. And when the atoms will be brought together, so the electrons of these atoms will be perturbed by the electrons and nuclei of adjacent atoms. So if there are 12 atoms around it, so it will we will have each atomic state that will be split into a series of closely spaced electron states. So as you can see, in that case, in this atom, each electronic state will be split in 12 states. And you can see that when this phenomenon occurred, so the interatomic distance decreases, the first electronic state that will be impacted will be the outer shell. So it is the one of highest energy that will first feel the presence of the other atoms. And when the atoms get closer, so the other electronic state will feel this the presence of these other atoms. And so this depends, of course, of what is the interatomic distance of equilibrium. Because if the interatomic distance of equilibrium is, let's say, here, so the electronic state 1s won't be disturbed, whereas the 2s will be. So we are explaining that each distinct atomic state will be split into a series. And as you can see, it will be a series of closely spaced electron states because all of them are very close one to another, but they remain discrete electron states. And so instead of describing, so this is another representation, but instead of describing the different energy states that are created by the splitting of the original electronic states, we are going to use another representation, which will be the one of electron energy band structures. So as you can see in that case, this graph is similar to the previous ones that we introduced. And so we should consider what is the equilibrium interatomic distance. And so let's say it is that one for these atoms. And so instead of representing all the discrete energy level, we are going to represent the energy band. And the size of the energy band will be representative of the different energies that the splitted electronic states have for this position in this material. And so, for example, in that case, since the interatomic distance is that one, here it says that the state, the electronic state 1s is not impacted. And so the level 1s remains the same, whereas the 2s and 2p are represented as electron energy band. And so this representation right here will be the one that we will use, the energy band structure. So at the beginning of this lesson, we introduced the energy band structure for isolated atom. And so in order to describe the electron energy states and their occupancy, we used 4 quantum numbers. So the first one corresponds to the shell and is defined by integers, so 1, 2, 3. And then we have the subshell designated by letters S, P, D. Then we have the magnetic orbital quantum number. And finally, we said that the fourth quantum number defines the spin of the electron. And so the electron will fill the states having the lowest energy, and each energy state will be filled by 2 electrons of opposite spin per state. So it is relatively simple. But of course, when we are talking about a solid, we should consider that it is formed by n atoms that are originally separated, but they are brought together in order to form material. And so let's see what is happening when the atoms are brought together. So first of all, let's consider that each of them are present at a high interatomic distance, and so they don't feel the presence of other atoms. And so, and let's consider that in that case, a solid is formed by other 12 atoms. And so, in this representation, we have the electronic state 1s and the 2s with distinct energy values. And when the atoms are brought together and come closer, we can see that first the electronic state 2s is impacted. In fact, it is these electrons are perturbed by the electrons and nuclei of adjacent atoms. And so this atomic state is splitted into a series of closely spaced electron states. So in that case, since it has 12 neighbors, adjacent atoms, we observe the splitting in 12 distinct atomic states. When the atoms are brought even more closer, we observe the splitting of other, of more inner energy electronic states. And so it is also splitted in 12 different states. So this is a very similar representation of what we presented. And so we should imagine that within this large band, in fact, we have discrete energy level, and it's not a continuous value of energy that the electron can occupy, but only discrete energy, but in that case it is represented as field. And so, of course, when we are looking to the interatomic distance, we should consider that in a solid, we have an equilibrium interatomic distance between these atoms. And so we should have a look of what are the energy, electron energy that are found in the material. So at this position, the energy level 1s is not impacted by the presence of the other atoms because it is the most inner one, closest to the nucleus. The 2s and the 2p are impacted. And so in order to represent the different, the range of value of energy that this electronic state is now taking, so we represent an energy band. So for 2s, it is represented right here in blue, and for 2p, it is represented in orange. And so instead of representing these energy levels and very detailed information, we are now going to use this kind of representation, which is energy band structures in a solid. And so, as we explained, the outermost electron layers is the more splitted because they are the most disturbed as the atoms coalesce. The electrical properties of materials are directly dependent on their energy band structure, and particularly on the arrangement of the outermost band and how they are filled with electrons. And so here are represented 4 kinds of energy band structure. And we are going to make the relationship between electrical properties of materials and their band structure. But first of all, in order to describe these band structures, we need to give some definitions. So let's first introduce the valence band. So it is the band that contains the valence electrons. So in the case A, we have some filled states, and after that, in the same band, we have empty states. Since here we find valence electron, we will name this band the valence band. Then let's define the Fermi level or Fermi energy, which is the energy corresponding to the highest field state at 0 Kelvin. So when there is no motion of electron, we define this energy level, so it is that one, which is the Fermi level, so the one that is occupied. So in the other case, it would be that one, and that one would be the Fermi level. After that, we have the conduction band. So the conduction band, it is the next higher energy band that is unoccupied at 0 Kelvin. So if the valence band is that one, so the conduction band will be that one. And if there is an energy gap between the valence band and the conduction band, which means there is some states that cannot be occupied by electron due to the energy band structures that we described previously. So we will call this space the energy gap or the band gap. So only the electrons with energies greater than the Fermi energy may contribute to the electronic conduction. So this means that these electrons can be accelerated in the presence of an electric field. And we call these electrons the free electrons. And so we are going to better describe and attribute this energy band structure to the different kinds of materials. So first of all, the 2 first cases are found in metals. So for example, the case A that we already described can be found in copper, whereas another kind of energy band structure can be found in other metals, for example magnesium, in which we have filled valence band and it overlaps with the conduction band. This is possible if we come back to this slide, if it's possible if we have a case that the equilibrium interatomic distance would be like here. In that case, you can see that you can have an overlap of one energy band and another one. And so in such kind of material, you have an overlapping of the valence band and the conduction band. Then in other materials that are not metals, we have filled valence band, so in these 2 cases, and an empty conduction band. And this case C corresponds to insulators, whereas case D corresponds to semiconductors. What is the difference between the 2? It is the value of the energy gap. So in insulators, this energy gap is higher. It is in fact higher than 2 electron volt, whereas in the case of semiconductor, it is lower than 2 electron volts. So now let's focus on the electronic conduction in metals, and in order to understand why they have a high conductivity. So in the two first cases that we described, we saw that we have empty energy states that are adjacent to filled states. So here, these empty states are in the valence band. So it is adjacent to this filled state. In that case, we have empty energy state in the conduction band. So metals are good conductors. They have high conductivities because they have a large number of free electrons that can be excited into empty state above the Fermi level. And so this electron turns to be free electrons and can contribute to the electronic conduction. And so what will make some of this electron in a field state be excited into an empty state? In fact, very low thermal energy will be enough to excite electrons, and when they will be excited, which means they will gain energy, they will be able to go to be excited to an empty energy state. And so they will tend to be in an energy state higher than the Fermi level, and so they will be able to contribute to electronic conduction because they will tend to be a free electron. And so now let's think about the movement of the electron in the materials. So if we consider these metals, so it are represented the ionic core and the free electron are represented in red, and we apply an electric field. So what do we expect to occur? So since we have a lot of free electrons, we should expect that in fact they would move, all of them would move, and we would have a continuously increase of the electric current. And so, in other words, we would have an electrical conductivity that will become infinite because all of the electrons would be able to move very quickly. But this, in fact, only occurs at 0 Kelvin in a perfect crystal lattice, because in fact, if we make a measurement of this electric current in order to determine the electrical conductivity, we will see that it will reach a constant value, and the electrical conductivity will reach also a constant value, which is a value that is reported in the table that we have shown previously. And so why is it the case? Because we have some frictional forces that are due to scattering phenomenon that hinder the acceleration of the electrons. What is a scattering event? So in fact, let's take this electron. It is accelerated by the presence of the external electric field, and it won't have a linear pathway. It will encounter this ionic core, and it will, so the direction, its direction will be changed, and as you can see, it will encounter many ionic cores, and so its movement, its direction in the material won't be linear, and in each scattering event, the electron loses kinetic energy. It is transferred to these ionic cores and so on in this representation, I mean. And this make that, this explains the frictional forces and why we have a fixed value for the electrical conductivity. And what can scatter the electron? In this representation, it seems that the ionic core are provoking the scattering events, but in fact, we have three things that can scatter the electron. So first of all, impurities. Impurity atoms, vacancies, interstitial atoms contribute to scattering the electrons. Then we have thermal vibrations, and finally, dislocations that are created by plastic deformation in metals. So we already described all these phenomenon in other lessons. So for example, impurities and dislocation are introduced when we talk about defect in metals, and thermal vibration when we talked about thermal properties. So to describe the extent of the scattering phenomena, we have this relationship between the drift velocity, which is Vd, which is the average electron velocity in the direction of the force imposed by the applied field. So since it is a negative charge, it goes in the opposite direction to the applied field, so it is going in that direction. And this drift velocity is directly proportional to the electric field intensity, but there is the factor of linearity is the electron mobility. And so the electron mobility, this parameter, will be an indication of the frequency of scattering events. So if this electron mobility decreases, this means that the drift velocity decreases also. So then we can make a relationship between the conductivity of most materials with this electron mobility, which is mu E. So you have the conductivity that is equal to the number of free electrons per unit volume, because we said that the electronic conduction is only permitted by free electrons. Only free electrons contribute to this. Then we have the absolute magnitude of the electrical charge of an electron and the electron mobility. So what impacts the conductivity? In fact, this is only the number of free electrons, so the number of charge portators, and the electron mobility. So now let's understand the effect of crystals defect on the electrical conductivity. So let's remember what we said. We said that crystal defects participate to scattering events. These scattering events are responsible for frictional forces that limit and counter the motion of electrons in the material, and explain why we have such a value for the electronic conduction, a fixed value. So in this table are reported for pure metals, but also for alloys, are reported the electrical conductivity. So as you can see, all of them are in the range of 10 to the power 7 ohm meter inverse. And now let's compare the value of the electrical conductivity for copper, which is 6 to 10 at the power 7, and of brass. So let's remember that brass, it is 70% of copper, 30% of zinc, and we have a substitutional alloy, the formation of a substitutional alloy, which is brass. And as you can see, in that case, when you have impurities that are introduced in copper, you have a decrease of the electrical conductivity, because as it is represented in a very schematic way in this figure on the right of the slide, instead of having a quite linear movement of the electron in the material, it increases the number of scattering events during its motion, and so it decreases the electrical conductivity. In the same way, we can compare the electrical conductivity for iron and for plain carbon steel and stainless steel. So for iron, we have 1 to 10 at the power 7 electrical conductivity, whereas for plain carbon steel, it dropped to 0.6, and for stainless steel, 0.2. So in this figure, you have a representation of what is formed if we mix iron with a very low percentage of carbon, which forms a plain carbon steel. You have the creation of interstitial alloy, and it is the same phenomena that occur. You increase the number of scattering events, and so the electrical conductivity is decreased. And in the case of stainless steel, you have a little bit more of carbon and other elements that are introduced, which decrease even more the electrical conductivity. Now let's talk about the effect of temperature on conductivity in metals. So we could expect that the electrical conductivity would increase with the temperature. Let's see what is occurring. So here in this graphic, you have the evolution of the electrical resistivity with the temperature. So we observe that there is an increase of the electrical resistivity with temperature, which means a decrease of the conductivity, which is quite contradictory with the fact that we have the creation of free electrons when we increase the temperature due to the thermal excitation of electron to level higher than the Fermi level. But in fact, when we increase the temperature, we increase the thermal vibration of atoms, and this increases the electron scattering. So the resistivity increases and the conductivity decreases linearly. As you can see, it is a linear relationship. So we saw that we have impurities that scatters the electrons and that increases the electrical resistivity, as well as thermal vibration. But we have also dislocation that are created by plastic deformation. And this is due to the fact that when you have a dislocation in your material, so it creates an obstacle for the electron and for their motion into the material. So you have these three contributions to the electrical resistivity. That's why we can write the electrical resistivity of a metal equal to the impurity resistivity, the contribution of the thermal vibration, as well as the contribution of dislocation or plastic deformation. So it is represented in this graphic. So the value of pure copper at 0 Kelvin, so without thermal motion, would be that one, equal to 0. But in fact, let's consider this temperature, minus 100 degrees C. You have a contribution of thermal vibration of the atom of copper. Then you have the contribution of the impurity. So in that case, we have introduction of certain amount of nickel. And then the contribution of dislocation or plastic deformation, which is that one. Okay, so the plastic deformation is during the processing of metal. It is created during its processing. Okay. So now let's talk about semiconductors and insulators. So let's remember, we have the valence band is totally filled with electron. We have an energy gap that is different in insulators and semiconductors. So it is higher than 2 electron volts in insulators and lower than 2 electron volts in semiconductors. And then we have an empty conduction band. And if we can excite an electron of the valence band to the conduction band, so it is able to drop to the conduction band. So we have the formation, or it results in a free electron that can contribute to the electronic conduction, and it creates a hole, which is vacancy in the valence band. Okay, so since the band gap is high in insulators, we have very few electrons that are excited across the band gap, and so that explains the low value of electronic conduction. Whereas in semiconductors, since the gap is lower, we have more electrons that can be excited across the band gap to the conduction band. Regarding semiconductors, we can distinguish two kinds of semiconductors. We have the intrinsic semiconductors, that electrical behavior is based on the electronic structure inherent to the pure material, and the extrinsic semiconductors, that electrical behavior is dictated by impurity atoms. What about the intrinsic semiconductors? So in that class, we find a silicon, which band gap energy is 1.1 electron volt, and germanium, which band gap energy is 0.7 electron volt. They are both covalently bonded, but we can also find ceramics composed of two different elements, which ionic character is higher. So when an electron is excited into the conduction band, we have a missing electron in this valence band. And if we think about the bond present in this material, we have a missing electron in one of the covalent bonds. And we have so a creation of a vacancy, which what we name hole, and we consider that a hole is a positively charged particle, which charge is 1.6 10 to the power minus 19 coulomb. And under an electric field, we have the position of the electrons that will move. So we have electrons that move, but also the missing electron or the hole are moving. So let's see what is happening. In this representation, we have the gray point as well as the red one that are electrons, and the green squares that represent the holes. So we have the movement of an electron that takes the place of a hole, and the hole that takes the place of the electron. Okay, so we have such kind of movement occurring. So we consider that, in fact, electrons and holes move in opposite direction under electric field. So electron moves in the opposite direction to the electric field, whereas the hole moves in the same direction as the direction of the electric field. Now, if we describe the electrical conductivity of intrinsic semiconductors, we have to consider that we have two charged particles that are moving and that are responsible for this conductivity. So we have the contribution of the electrons, as we saw in metals, but we also have the contribution of hole. And so since in this material we have the same number of electrons in the hole, we can write the conductivity in that way. Okay, so this is the electron mobility, this is the hole mobility. They have different value, but the number of them are equal. So that is why we have this simplification of this equation. Now let's talk about extrinsic semiconductors. In fact, most commercial semiconductors are extrinsic, in that material we introduce impurities that have an excess of electrons or an excess of holes, and the electrical behavior depends on the kind and on the concentration of these impurities. And we will distinguish two types of extrinsic semiconductors. We have the N-type, in which we have an increased number of electrons, and the P-type, when we have an increase in the number of holes after introduction of these impurities. So the most common example of N-type semiconductors are silicon lattice. So when we look to the electronic configuration of silicon, we saw that a silicon atom has 4 valence electrons, and these valence electrons are involved in covalent bonding. So each silicon atoms create 4 covalent bonds with 4 silicon neighbors. In that case, there are no free electrons that could contribute to the electric current, and so it results in an insulator rather than a semiconductor. And so if we want to turn it into a semiconductor, we can introduce impurities called doping. And for example, phosphorus is an adequate impurity, but we can also use other elements as phosphorus that in fact possess 5 valence electrons. So in that case, let's take the case of phosphorus. We have phosphorus that becomes a substitutional impurity. That means that it will take the place of a silicon atom in the lattice. And within these 5 valence electrons, we have 4 of them that contribute to covalent bonds with the neighbored atoms, and we have 1 loosely bound electron to the phosphorus atoms. And this loosely bound electron can easily be excited to the conduction band and become a free electron, and so it can contribute to the conduction of electricity. So phosphorus, let's have a look to the movement of this free electron. So we have this red electron of phosphorus that can move from one atom to another. So it's become neighbor of silicon and moves in the material, so it moves in the opposite direction as the direction of the electric field, and in that case phosphorus is a donor, it gives an electron. So it is an example of an N-type semiconductor. In order to explain what is happening in this N-type semiconductors, we can have a look to the energy band structure. And as you can see, there is a donor state within the energy gap, which is due to the impurities that has been introduced in the material. So in that case, it is the 5th electron, valence electron of phosphorus. And this donor state is right below the conduction band. By thermal energy, it can be easily excited and it jumps into the conduction band. And so we now have a free electron that can conduct electricity. And so in the N-type semiconductors, the electrons are the majority carriers. That means that the electrical conduction is due to the displacement of electron, to electron motion. And so the conductivity of N-type semiconductors can be written in the same way as we wrote the one for metals. Since the number of electrons is much higher than the number of holes, we take into account the number of free electrons and the mobility of this electron into this semiconductor. Now let's talk about P-type semiconductors. So in P-type, we increase the number of holes. So in that case, let's take the same silicon lattice, we will introduce an impurity, also called doping, but in that case, we will choose a substitutional impurity that will have a lack of electron. So, for example, barium has only 3 valence electrons. All these 3 valence electrons will contribute to covalent bonds with other neighbors of silicon, and we will have one electron missing, and so we can see this electron missing as a hole. And so when we consider this hole, we can also consider that this hole and another electron from adjacent bond can exchange their position. So if we apply an electric field to this material, we have this electron right here that will fulfill this hole, and this hole that will move to the original position of this electron. And so in that case, we can consider that the hole is moving and conduct electricity. If we have a look to the energy band structure in this kind of material, so in that case, we have a state that is created by this doping element that is within the energy gap, and that is close to the valence band. And so, so this acceptor state is right above the top of the valence band, and by thermal energy we have this valence electron that can move to this acceptor state, and it creates a hole in the valence band. And so in that case we will consider that this hole is going to move, and that's why for semiconductors of P-type, the holes are the majority carriers. We have a higher number of holes than number of electrons, and so the conductivity is considered to be due to the movement of this hole. So it depends on the number of holes that have been introduced, and it depends on the mobility of these holes that are, let's remember, a positive charge carrier. And so in that case, the impurity is called an acceptor because it creates a state that accepts an electron from the valence band. So that's why in that case, we have introduction of acceptor as doping elements. Finally, let's have a look to ionic ceramics and polymers. So most of them are insulators, which mean that the energy gap between the valence band and the conduction band is quite high, superior to 2 electron volts. That's why even by thermal energy, only a very few amount of electron will be excited up to the conduction band. And but in ionic ceramics, we should take into account that we have charge carriers that are anions and cations, and there is a possibility of migration and diffusion of these charges in the presence of an electric field. And since they have opposite charges, electrical charges, so the diffusion of anions and cations occurs in opposite directions. So in fact, in this kind of materials, we have the conductivity, which is equal to the electronic contribution, so electronic conductivity, and also the ionic conductivity. And any of these contributions may be predominant, and it depends on the material and the purity, but also on the temperature. And in this table are summarized typical values of electrical conductivity for ceramics and polymers. So let's first have a very quick talk about graphite. So graphite is composed of carbons that are organized in layers. And in these kind of materials, we have free electrons that can move within these layers very easily. And that's why it gives rise to a rather high value of electrical conductivity. Whereas for ceramics and polymers, you can see that all these materials are insulators, which mean have electrical conductivity lower than 10 to the power minus 10 ohms meter inverse. Most polymers are insulators, but some can be made conductive either by introducing an additive to the polymer. For example, we can introduce conductive particles to create a composite. These particles can be graphene, or can be carbon black. And so by controlling the amount of particles and the kind of particles, we control the conductivity, and we can modify the conductivity of these polymers. Or we can create polymers with inherent conductivity by doping. So an example of conducting polymers are polypyrrole, polyaniline. here you have the chemical structure of polyaniline. So in that shape, it is not conductive, but by doping with hydrogen chloride, we transform it into a conductive polymer. As you can see, you have some charges along the polymeric chains, and these charges can move along these polymeric chains upon the application of an electric field. And the application for these conductive polymers are polymeric battery, but also gas sensors, biosensors, and so on. Here you have a very simple scheme of a gas sensor. So this polymer wire is conducting. It is made of one of these polymer or a blend of this polymer and another polymer. And when the gas enter in contact with the polymer wire, it decreases the resistance, it decreases the conductivity. And by adding some electronic here at the two sides of this polymer wire, we can detect the change of the conductivity of the polymer, and this gives us the information of the detection of the gas. So it is a gas sensors. And in 2000, the Nobel Prize in Chemistry was given to 3 researchers for the discovery and the development of conducting polymers. So now you know some important electrical properties of materials, such as resistivity and conductivity. We described the mechanisms and the particles that are responsible for electrical conduction in the different classes of materials. And we made the relationship between the electronic band structure and electrical conduction in metal, semiconductors, and insulators. And so now you know that for a specific application requiring either insulating properties or electrical conductivity, you have a notion of which kind of material would be more appropriate for this case. Thank you very much. I hope that you learned a lot about electrical properties of materials. Here is my email address, so if you have any question, you can write me, and it will be a pleasure to answer it. Thank you very much.